So whether the slides are visible to everyone? Hello?
Yes, sir, they're visible.
Yes, sir.
Okay. Okay. So in the last class, we started looking at the heat transfer when there is a boiling and condensation is taking place, isn't it? So we started looking at first boiling. Again, we have discussed that whenever there is a boiling or condensation, whenever there is a phase change is taking place, usually the heat transfer coefficient is higher than the usual convection and the conduction which we see. Okay, the reason behind that is in usual convection, the heat transfer mostly takes surface to the bulk of the fluid, whereas in case of boiling or condensation, the heat transfer mostly is restricted in a very thin layer close to the surface, and therefore since the thickness of this layer is much smaller, the heat transfer coefficient is much higher compared to that in a usual conduction and convection. Okay. Again, then we have looked at this boiling curve. So there are three main regions: interfacial evaporation, nucleate boiling, and film boiling. Interfacial evaporation is there when the degree of superheat or the excess temperature T is in the range of 0 to 2, isn't it? So it is above the saturation temperature, but the temperature is only 2 degree, maximum to 2 degree above the saturation temperature. We see the interfacial evaporation. So where mostly the evaporation takes place from the surface of the fluid. After that, there is a nucleate boiling regime where the small tiny bubbles starts forming in the liquid, and this region is from the excess temperature 2 to 35, and again between this region there are two small regimes are there. So B2C, there is a one regime where you can see there is a bubble formation takes place, but even the bubble formation are taking place, but these bubbles are not escaping at the surface. Even before they reach to the surface, they collapse in the liquid. Beyond this C, there is a stable bubble formation takes place. So between C and D, you will see that the stable bubble formation takes place, and these bubbles then escape from the surface. Okay. So mostly industrial operations has to be performed only in the nucleate boiling regime, because in this particular regime you can see the highest value of the heat transfer coefficient you can get. You can clearly see in this particular figure the highest heat transfer coefficient you can see only in the nucleate boiling regime. But when we cross this nucleate boiling regime, there is a film boiling regime starts. In this particular regime, what happens is, so this jet of bubbles which starts from the surface, this starts coalescing around the heating surface itself, and they starts forming a film around the heating surface. And since this film of gas is formed over the heating surface, the heat transfer coefficient initially drops. So from D to E, there is a drop in the heat transfer coefficient takes place because of the film formation over the heating surface. Beyond this, beyond the point E, the radiation starts dominating, and therefore the heat transfer coefficient further increases. But as I said, here even though heat transfer coefficient is higher, but the temperature difference or excess temperature required is very high, and therefore only the nucleate boiling regime is the regime where all the process equipment has to be operated. Okay, so this is what we have seen in the last class. So this discussion I will not go again. This I have gone couple of times. This thing is also we have seen. So we can find out what will be the size of the bubble, a stable size of the bubble using this particular formula. So how much degree of superheat is required, that we can calculate by this equation 1 for a particular size of stable bubble. Okay, so in this particular equation, everything are known in general. So the sigma is nothing but the surface tension, T sat is the saturation temperature, PL is the liquid pressure, LV is the latent heat of vaporization. So everything is more or less known, and based on that we can find out if you wanted to have a particular size of stable, in that case how much degree of superheat above the saturation temperature is required, that we can calculate using this. Again, the prediction by this equation is slightly over prediction in a sense that the stable bubbles forms even a lower value of superheat, because this particular equation is for homogeneous nucleation. So that means nucleation takes place only in the liquid. That is what is been assumed here. But in a real life scenario, the surface cavities which are present, which initiates the formation of the bubble, and therefore the stable bubble formation takes place even at a lower value of superheat. Okay. Again, we have seen several correlations. So we have seen the correlation mostly for the nucleate boiling regime. The important correlation is a Roshanov correlation. So that is the more accurate one. Then there is a Mostinsky correlation, which is simple but is not accurate as the Roshanov correlation. Again, you can get the order of magnitude of the heat flux or the heat transfer coefficient using Mostinsky correlation. Again, whenever you are designing the heat transfer, boiling heat transfer, basically you wanted to know where that limit of pool boiling ends, isn't it? Sorry, this nucleate boiling ends. So that Q max, so maximum value of heat flux corresponding to the highest point in that boiling curve, that particular point we wanted to know a priori in order to design our heat transfer equipments, so that my heat transfer remains in the nucleate boiling regime, and therefore the correlation for the critical heat flux is also given. So these are some of the correlations. There's a Joubert correlation, and then there's another correlation by Lenhard. So using this, you can find out what will be the maximum value of the critical heat flux. Typically for a water case, the critical heat flux occurs around the excess temperature of 35. But for a other liquid, you have to find out using the correlations. Again, because of some reason, if you wanted to operate in a film boiling regime, in that case, the correlation one has to use is, these are given here. So these are mostly such situations mostly takes place in a nuclear power plant where large amount of heat is generated, and therefore you will not be able to restrict your boiling only in the nucleate boiling regime. So in such cases, even the film boiling is taking place. So the correlations given in the film boiling are given here by Bromley. Again, as I said, that in a film boiling regime, the radiations also starts dominating, and therefore one has to account both radiation as well as the heat transfer corresponding to boiling. So this can be accounted using this particular equation. So these are the correlations which we have seen. So I have partially gone through all your comments. One of the comment people have given is lot of correlations are there, but the good thing is that all the correlations ends at this chapter. After this there is no correlation. Okay, so probably these are the last correlations, and there are no correlations after this. And remember, what is the rationale behind these correlations? I said it in the starting itself. If you wanted to solve the heat transfer problem without these correlations, that means what? You have to solve the momentum transfer and then the heat transfer both. But by using this correlation, you are eliminating the solving momentum transfer, and you can directly go to the heat transfer. Okay, so you are simplifying your analysis by using these correlations. But of course, you can get rid of these correlations and you can formulate your actual problem. The question is whether you will be able to solve it on a computer or not. Okay, that is the question. But if you can able to solve it, then you don't need correlations. Okay. Okay. So this problem we have seen in the last class. I will not go through these again. So in a forced convection boiling, so this is the example of a forced convection boiling. So there is a subcooled liquid is coming in this particular container, and this container is being heated from the border here. So this border and the another border is being heated at the temperature of, let's say, TW, and TW is higher than the saturation temperature. Okay, so in this case what you will see that there are different regimes are there. So initially in the bottom you will see the subcooled boiling regime is there up to this. Okay, after this the bubbly boiling starts, then there is a slug flow is there. Again further if you go up, you will see that the vapor film starts only at the the surface of the wall itself, and this is something called as annular flow. Then again if you go at the top, there is a mixed flow, and after that there is a single phase vapor flow. So these are the different regimes are present when we are looking at forced convection boiling. Why we are saying a forced convection boiling? Because this liquid is being pumped through a external force here, and based on that the vapor is coming out. So it's not a natural convection. Okay, so this is what all about the forced convection boiling. There are some more details and correlations are given about forced convection boiling, but we will not go through those in this course. If you wanted to get more information, you are free to get more information from the book. Okay, so let us start with the today's class. So far we have concentrated only on boiling. Okay, now there is another important phenomena which is a condensation. So that means the phase change from vapor to liquid. This is also very much important in the process industry, because you will see condensers used in the distillation column. You will see the condensers used for cooling the reactor and all, isn't it? So condensation is also a very important and a important phenomena in the process applications. Okay, so condensation means the change of phase from vapor to the liquid. If the mixture of the vapor and gas is cooled, the vapor condenses to form a minute droplet suspended in the carrier gas. This is called as homogeneous condensation. So homogeneous condensation is nothing but formation of the droplet in the liquid itself, in the carrier gas itself. Okay, but when this condensation takes place on some surface, on some cool surface, then that particular condensation is referred as surface condensation. Okay, so in contrast, if a vapor or a gas vapor mixture comes in contact with a cool surface, condensation occurs on the surface, and this is referred as surface condensation. Okay, again so in mostly the practical application you will see the surface condensation. So in a surface condensation, if the surface is wetted by the liquid, in that case there is a formation of the continuous film takes place, and this type of condensation is referred as film condensation. So here this word wets is very important. Okay, when the condensate wets the surface, it flows down as a continuous film as shown here. Here you can see the film of the condensate liquid is flowing downward here, isn't it? So there is a continuous film is there, isn't it? So this type of condensation is called as a film condensation. So this is the naturally, if you see most of the condensers, this work based on this particular phenomena. But there is another type of condensation which is also referred as which is referred as drop wise condensation. So whenever the condensate do not wet the surface, so if the surface is not wetted by the condensate, drops instead of continuous film appears on the surface. So as you can clearly see here, there is a drops of the liquid are formed on the surface. So there is no continuous film. So vapor is coming in contact with the surface, cool surface, and it starts forming the drops like this, but there is no continuous film. And this type of condensation is referred as drop wise condensation. So this occurs when the surface is contaminated or the condensate liquid does not have an affinity for the surface. Okay, so what is important to note down here is film wise condensation is more commonly occurring phenomena. Drop wise condensation is not that common, but if you look at the heat transfer coefficient in a drop wise condensation is much higher than the film wise condensation. This one everyone has to remember that the heat transfer coefficient in a drop wise condensation is much higher compared to the film wise condensation. Reason behind that is, here you can see at several locations, here you can see the gas is directly in contact with the cool surface, isn't it? So gas is directly contact in the cold surface here, isn't it? But in contrast with that, if you look at the, if this gas has to, you know, form of film, and therefore the heat transfer coefficient in a film wise condensation is lower than the drop wise condensation. You may ask that why people then use a film wise condensation more regularly and why not a drop wise condensation, isn't it? So the reason behind that is the drop wise condensation. For a drop wise condensation, you need to modify the surface. So you need to add a oil or a surface modifications for that, and that may contaminate your condensate. That is the first reason. Again, a precise control of the surface is required, which may not be possible when you are looking at the industrial process. So that is the reason why a film wise condensation is more common compared to a drop wise condensation. Okay, is it clear to everyone? Hello?
Sir, can you please explain the difference in surface condensation and film condensation once again?
So as you can clearly see in the figure, in a film wise condensation, whenever these vapor particles come in a contact with the cold surface, basically the film of the liquid starts forming. This film then okay, but in contrast to this, if you look at a drop wise condensation, in a drop wise condensation, instead of forming a film, instead of forming a continuous film as shown in a left hand side figure, the drops are formed. Drops are formed. Why? Because the surface property, that the surface, if the surface is not wetted by the condensate. So when this will is possible, whenever the surface is oily, or whether the surface is having a different surface tension, something like that. So in such cases only the drops are formed. Otherwise, in most common phenomena is a film wise condensation, where the condensate forms a continuous film. Okay, so in this case there is no continuous film, only the drops are formed at distinct location, and in between there is a free spaces as shown here. Okay, correct? Is it clear? Still not clear?
Yes, sir, it's clear now.
Okay, so in this case, again, a most common phenomena that is used in a process industry is a film wise condensation, because in addition to condensation, the purity of the condensate is also important, isn't it? So in this case, basically you need to contaminate that. So that is not desirable, even though the heat transfer coefficient is very at least 2-3 order of magnitude higher than the film wise condensation, still it is not advisable. Okay, clear? Okay, so let us move to the analysis of that, analysis of the film condensation on a vertical surface. So there is, let's say, vertical surface is there. So TW is lower than the saturation temperature. So TV is the vapor temperature. Okay, and there are different assumptions we have used here. So the condensate film is fully developed laminar flow with a zero interfacial shear and a constant liquid property. So what it means is, if this film is there, this condensate film is there, so properties of the liquid in this particular film are uniform. Also, what we are assuming that this particular film is fully developed, that means the wall effects are neglected. In this particular case, the vapor is assumed saturated, so this vapor is assumed saturated. So only the latent heat of vaporization is coming into the picture. There is no sensible heat coming into the picture in this case. That is what it means from the second assumption. The heat transfer through the condensate film occurs by a conduction only. So heat transfer, remember, there is a vapor here, and then there is a cold surface is there here, isn't it? So between this cold surface and this vapor, the heat transfer is taking place through this film, liquid film, and this liquid film, the temperature profile is linear. So what we are assuming that the heat transfer in this particular film is taking place only by conduction. That is what we are assuming. Okay, in conduction you can get the linear temperature profile, isn't it? If there is no generation, if there is no accumulation, isn't it? That is what we have seen in the first chapter. Correct. So the third assumption is this film linear, and the last assumption is, remember, this is the x direction, this is the y direction, and the z direction is across the plane as we perpendicular to this plane. So along the z direction, the thickness or the width of this particular plate, we are assuming a very large width of the this plate along the z direction. So again we are assuming that there is no variation in the z direction, so there is no variation in the z direction. So this uniform film as shown here is same across the z direction. Again, for a simplicity, we are calculating everything per unit width of per unit width of this plate along the z direction, and therefore we are assuming this width along the z direction as 1. So you may say that here we are saying a very wide, and then we are saying unit. So basically what we are doing, calculating everything as per unit in a z direction. Is it clear to everyone?
Sir, I wanted to ask what zero interfacial shear
Is
means
it
in the
clear?
first.
So at this surface of this liquid film and the vapor, there is no shear here at this interface. Get it? Hello? So there is no shear force offered by the vapor on a liquid. That is what it means. In a liquid, in this liquid, there will be a shear. That is why we are assuming a shear force here. But there is shear force at the interface here. All right?
Yes, sir.
Okay. So again, clearly in this case you can see from the starting from this leading edge, as we move along the x direction, you can see the thickness of this condensate film is going to increase, because more and more vapor is going to get condensed, and this will accumulate in these particular films, and therefore the thickness of this film will keep on increasing, isn't it? That is one thing, correct? And therefore this area, uh, in this case therefore in this case we have to make a shell balance, because the thickness of this film is going to continuously increase as we move along the x direction, because more and more condensate is going to get accumulated in the film, and which is going to increase the width of this film as we move down. Okay, so in this case definitely we have to make a shell balance. So let us consider this particular shell. Maybe I just put this with a different okay, so okay, so this particular box is the shell. This particular box is the shell. Okay, and the thickness of this dx and the width of this particular shell is very small, and therefore even though there is a curved surface here, but you can still consider this as a rectangular box. Is it clear? Is it clear? Not clear?
Sir, it's clear.
Okay. So now let us make a force balance here. So what are the forces acting on this particular element? So this particular element is at a distance y from the wall, and the thickness of this particular element is delta minus y, because the thickness of the film is delta at this particular location, let's say. So delta minus y is the thickness of the this element here. Okay, and the forces acting forces acting on this particular element are, so there is a shear force which is acting upward direction, because that is going to oppose the movement of this particular element downward, isn't it? This element is going to move downward because this liquid is flowing downward in a film, isn't it? So shear will be acting in a upward direction, shear force will be acting in a upward direction. Similarly, the weight of this particular element will be acting in a downward direction, so that will give you a gravity, isn't it? And since this element is moving in a downward direction, the vapor will oppose its movement in a downward direction. So in a upward direction, there is a buoyancy force. There is a buoyancy force in upward direction. So we can make a force balance, which in this case is going to be F1. Shear force is given as F2 minus F3. So that is going to be the force. We can put all the individual forces in their usual terms. So shear force can be given in using a Newton's law of viscosity. So Newton's law of viscosity is given here as minus mu du by nothing but the gravity force. So that is rho L into G into so delta minus y into dx, that is going to be the area, isn't it? And multiplied by the width in a z direction. Since width in a z direction, we are assuming t. Therefore, in this particular part, the gravity force is given as rho L into G. So rho L into G is, rho L will have kg per meter cube. G is acceleration due to gravity, per meter cube is there. So therefore definitely you have to multiply here by the volume. Then only you will get a force balance in mass into acceleration. So the volume in this case is going to be dx delta minus. Is it clear? Similarly, the buoyancy force will be again given as rho v, since the vapor is going to oppose the movement of this particular fluid element which is coming downward. So therefore rho v into g delta minus y into dx and multiplied by 1, so that 1 is omitted. So this we can rearrange. So after rearranging, what we get is rho L minus rho v g delta minus y into dx. So that is what the expression we are going to get it. Okay. Now, from this particular equation, we can integrate this particular equation to calculate the velocity profile at any location y, isn't it? So any location y, what will be the velocity profile across the this y, across this y, that we can find out directly by
Hello, sir.
integrating this particular equation. So delta x will get cancelled out and we can everything and integrate it.
So you're not clearly
Hello?
audible.
Hello, am I not clearly audible? Let me just check. I am not audible now.
Sir, it's okay
Hello?
now.
So sometimes this internet in IIT is now messing up big time.
Hello,
So
sir.
please stop me if I'm not. Yes, please go ahead.
Can you explain the direction of buoyancy force?
See, in this case, what is buoyancy force? Buoyancy force is the force. See, the vapor is there here, isn't it? Vapor is there outside here. Outside of this film, there is a vapor, isn't it? Correct?
Yes, sir.
So now this particular element, which is the liquid element, which is moving in a down, isn't it? So there will be opposition by this vapor which is present on the right. So this is what is accounted here, isn't it? So as this liquid is coming down, coming down because the vapor is getting condensed, isn't it? So the size of that is going to increase. But at the same time, as it is coming down, it is opposed by a vapor which has to move in a upward direction, isn't it?
Sir, I think the arrow should be in the other direction then for F3 in the
Oh,
diagram.
I am really sorry. I am really sorry that I messed it up. I'm sorry. This arrow I messed it up. Yes, yes. I'm really sorry. I have messed it up. I will just do it, correct it. Okay. Just a minute. Not right. Okay. So now in this particular case, we can integrate this particular equation with respect to y. So by doing that, we can find out how the velocity is distributed across the y direction. So that is obtained as after integration, what you get is rho l minus rho v into g divided by mu l, and there is delta here. So delta y minus y square by 2 plus c. So where c is the integration constant. Again, we can use the boundary conditions here. So boundary condition at the wall, there is a no slip condition here at the wall. That means at the wall velocity is 0. So as y equals to 0, u equals to 0. So if you minus rho v z divided by mu l y delta minus. Now this is the velocity distribution across the y. Now flow rate of the condensation. So mass flow rate is obtained. So velocity multiplied by cross sectional area. Velocity multiplied by cross sectional area multiplied by in this particular case, we are looking at the element, isn't it? In terms of the x at any location x, if you look at this velocity profile, we have obtained only for, and as we move from x equals to 0 to as we are moving from x equals to x, this delta is varying, isn't it? So in this case, the mass flow rate at any location x can be obtained as integration 0 to delta this u as it is multiplied by cross sectional area. So cross sectional area in this case will be what? The cross sectional area from the top, isn't it? So cross sectional area from the top is going to dy into thickness in the z direction. So that is 1, isn't it? So into u. So if you put it in this particular equation multiplied by rho l is nothing but the density of the liquid. So if you put it in this particular equation and integrate, what you get is rho l as it is, and this u we can replace by this. So you replace this here in this case, and if you want to get it is rho l rho cube divided by 3 mu, but this is nothing but the mass flow rate at any location x. So this is the mass flow rate which we have obtained from the velocity profile here. Okay. Now again, in this case, the delta is the thickness of the condensate film at that particular location x. As x increases downward, now here the same argument we can say as we are moving from x equals to 0 to any value x in a downward direction, basically more and more vapor is getting condensed, and therefore the thickness of the film is going to increase. Thickness of the film is going to increase, isn't it? So clearly, more and more vapor is going to get condensed means what? There is a heat transfer taking place. So amount of heat transfer taking place has a direct relation with how much is going to be the increase in the thickness of the film. Okay. So that is what is being given here. As x increases downward, the film thickness also increases because of condensation of more vapor. The rate of condensation on the elementary surface of psi into 1 exposed to the vapor can be obtained from the rate of heat transfer through this area. The temperature profile in the condensate film is assumed to be linear. Clearly. So in this case, see, on this particular element, maybe I just go back here. On this particular element, the amount of heat transfer is taking place from what? From this direction. From this direction, the heat transfer is taking place, isn't it? So what is the cross-sectional area? Cross-sectional area is going to be this, dx into a z direction, that is 1. So dx into 1 is going to be the cross-sectional area. So cross-sectional area multiplied by the temperature gradient, isn't it? dt by in this case, what the temperature gradient is going to be, dy. But since we are looking at the entire, this particular element, so this will be delta, and the temperature difference in this case is going to be Tv here and Tw here. So the temperature difference Tw minus Tv is going to be the temperature difference across this length divided by delta is going to give me the temperature gradient. Temperature gradient multiplied by the cross-sectional area. This cross-sectional area will give me the amount of heat transfer taking place between this vapor here and the wall here. So that is what is being used here. Okay. So the rate of heat transfer will be given as K, that is the thermal conductivity of the liquid, into Tv minus Tw, that is the temperature difference divided by delta. So this is entire thing is coming from Fourier law of heat conduction multiplied by area. So area in this is going to be dx into 1. And now this is the rate of heat transfer. Now rate of heat transfer, that is the amount of heat is transferred from the vapor to the cooler surface, isn't it? Between the cooler surface and the vapor. Okay, and this amount of heat transfer is resulting in the condensation of the liquid. That means if you divide this rate of heat transfer by a latent heat of vaporization, what we are going to get is the amount of vapor that is being condensed at that particular, isn't it? So that is what is being done here. So rate of heat transfer, we have obtained this, and this rate of heat transfer, if we divide this rate of heat transfer by the latent heat of vaporization, so what we are going to get, the amount of vapor being condensed in the element. So that is what is given by dm here. Okay, so this is equation number 2. Now this equation which is giving me a mass flow rate, this is also giving me a mass flow rate in an element, isn't it? In a differential element, what is the mass flow rate that we have obtained, isn't it? Now the same thing we can obtain from here also. This is the equation number 1 which gives me a mass flow rate. I can differentiate this equation, I will get dm, isn't it? This, both these mass flow rates are same. So from equation number 1, this is what the mass flow rate I have obtained. I can differentiate it. So this becomes dm. Dm is obtained as rho L minus rho v divided by 3 mu L as it is. This is the constant term, isn't it? Since as we are moving, as the x is moving, in this case, this is with respect to x, isn't it? So as x is moving, only the change in the delta is taking place, and therefore we will have 3 delta square into d delta. So differentiation of delta cube will give me 3 delta square into d delta, and this is equals to this 3 will get cancelled out. So what we will get is rho L in the bracket rho L minus rho v g delta square divided by mu L into d delta, and this is same as what we have obtained from the equation number 2. So this dm is same. So we can put it in this equation. So rho L into rho L minus rho V G delta square mu L into D delta is equals to KL TV minus TW delta LV into dx. So what this equation gives me? This equation gives me, as I increase the distance x, how my thickness of my condensate film is going to increase or decrease. That is given by this particular equation, and this is been given in terms of the element, and therefore we have to integrate this further. So if we integrate this further, what we get is rho L rho V rho L into rho L minus rho V G mu L. This is taken as a common, and integration 0 to delta, this becomes okay. So this delta is there on the left hand side. This is moved on the right hand side. This is moved on the left hand side. That is why this becomes delta cube. So this becomes delta cube d delta 0 to delta, and on the right hand side KL TV minus TW divided by LV, and again integration between 0 to x dx. Okay. So if we integrate this, what we get is rho L minus rho V G delta raised to the power 4 by 4 mu L okay, sorry, some small mistake was there. Okay, so after rearranging, what we finally get is delta x is obtained as 4 mu L KL, where KL is nothing but the thermal conductivity of the liquid, x TV minus TW divided by LV rho L minus rho V G, and raised to the power 1 by 4. So this is nothing but the thickness of the film at any location x, from the leading edge. So what it means is, if I move from this leading edge, what will be the thickness at any x? That is obtained by using this particular equation. Okay, so this is a local thickness. That is why this is delta is given as a function of x here, isn't it? Based on this, now I can find out the heat transfer coefficient. Remember, heat transfer coefficient is what? Heat transfer coefficient is given as KL by delta, isn't it? KL by delta. That is what we have seen from the film theory. So that is what is been calculated here, isn't it? H is given as KL by delta. So again, this KL and delta we have already obtained from this. We just divide it here. So by rearranging, what we get is this LV rho L minus rho V G KL cube divided by 4 mu L x TB minus TW and raised to the power 1 by 4. Again, from this we can find out Nusselt number. Again, this is the local Nusselt number. That is why it is given NUX. This is given as HX by KL. HX by KL. So this is what we have obtained here, isn't it? So LV rho L minus rho V GX cube divided by 4 mu L KL TV minus TW raised to the power 1 by 4. This is going to be the Nusselt number, local Nusselt number. Now again, see, remember up till now we have only find out the local heat transfer coefficient, local thickness of the film, local heat transfer coefficient HX, and local Nusselt number, isn't it? Now we can find out the average heat transfer coefficient over the entire length of the vertical plate. If we consider that the length of this entire plate is L, in that case we can find out the average heat transfer coefficient directly by integrating this particular equation H across the length. So that becomes 0 to L integration H dx divided by L. So after integrating, what we get is 0.943 LV rho L minus rho V GKL cube divided by mu L into L TV minus TW and raised to the power 1 by 4. One important thing to note down here is there is a mistake in the book. Okay. So there is a factor of 4 is given here in the denominator in the book, which is not correct. Please, there 4 is given in the book in the formula printed in the book, that is not correct. So the formula which I am giving you is correct. In the bracket, this all these things without the 4 in the denominator here. So 4 is here, but this 4 is already accounted while calculating this 0.943. So 4 by 3 into this 4 raised to the power minus 1 by 4. So that total becomes 0.943.
Hello,
Okay.
sir.
Hello, sir. Yes.
So why have you written the Nusselt number equal to h?
What? Why?
Sir, in the local Nusselt number, the expression I have written nux is equal to h.
Sorry. I'm just correcting. Is it all right now?
Yes, sir.
Okay. Now one more thing to note down here is whenever we are looking at condensation, all the properties has to be calculated as average temperature. And what is the average temperature here? Vapor temperature plus wall temperature divided by 2. This one has to remember. Okay. So this is the final formula 0.943 LV rho L minus rho V GKL cube divided by mu L capital L into TV minus TW and raised to the power 1 by 4. Okay. Now, so far we were looking at the vertical film. Okay. Vertical film and the laminar flow we were considering. Remember, all this derivation is based on the laminar flow. That is why we have used that mu du by dx we have used, isn't it? Du by dy we have used here, isn't it? So this is only for laminar, isn't it? So only the laminar flow we have considered. So for a turbulent flow, the correlations are already given in the book. I have not noted down here. Okay. For a laminar flow, again, the condensation can take place on the outside film, outside tube. So in this case, you can see the condensation is taking place on the outside of this plate, isn't it? Outside of the plate. So whenever we are looking at condensation outside, single tube we are using. If we are considering a horizontal tube, unlike the vertical, plate or vertical tube we have considered so far. Unlike that, if we consider a condensation outside the tube with a horizontal tube, for a single tube, the correlation given as 0.728. So this is 92. Remember, in earlier case it was 0.943, but instead of 943, the difference here is 0.728. And instead of capital L here, the diameter of the tube is used. Diameter of the tube D is used here. Unlike in an earlier case, it was L. Capital L was there, isn't it? Again, this you can derive. This particular expression one can derive in a similar manner. Okay. Now, unlike a single tube, if suppose there is a bank of the tubes and there are tubes over one above another, so in such cases, if there are n tubes placed directly over one another, in that case the expression one has to use is 0.728. But here n, capital N, this is the additional factor coming in with respect to this particular formula. So what is this n? N is not the total number of tubes. Remember, if there are 100 tubes are there, and if you are having three columns, maybe 10 columns are there, so each column will have 10 tubes over one another. So this n is going to be 10. It is not going to be 100. It is not going to be 100. So don't get confused with this. This n is the tubes placed directly over one another. This is a very important word. Don't get confused. Maybe I'll just explain it a little bit more. So what I am trying to say here is, suppose if you are having a horizontal tubes like this, arranged one another like this. Okay. So what will be n here? What will be n here? N will be 2. N will not be a 4. Okay. So one above another, there is only 2 tubes are there, isn't it? In this manner. So this n is 2. Is it clear to everyone? Hello? Hello?
So
Is it
basically
clear?
it means the number of rows, right?
Yes. Number tubes in each tubes in each column. N is a number of tubes
Yes.
in each column. Okay. Perfectly all right. Okay.
Yes.
In a sphere, the again formula is same except that this constant is 815 and all these expression you can derive. I am directly writing it. These are not the empirical correlations. These are derived from the velocity profile. These are not the empirical correlations. Okay. Okay. In a similar manner to this is now a condensation outside, but there are the cases where condensation inside is also important. For example, your air condition. What happens in the air condition? The condensing fluid or the refrigerant, whatever is used in the AC, that get condensed inside the tube, isn't it? That get condensed inside the tube in a refrigerator or even in a so condensation inside the tube is also a very important phenomena. Okay, so in all such cases the equation one has to use is this. So one has to use 0.555. This is the same expression except that here LV double dash is used. LV double dash is sorry. So LV double dash is nothing but the latent heat of remember here in this case the latent heat of vaporization is used like this. So note down here is that when we are looking at the condensation inside the tube, in this case we are not assuming that the vapor is in a saturated, so there is a degree of superheat is also present. That is why this particular fraction, this is going to give me the this is going to give me a sensible hit, isn't it? And this is just a latent hit. Correct? Is it clear to everyone? Is it clear?
Yes, sir. So could you
Okay.
explain by why we have to use LV double dash in this case?
So here in this case, we are not assuming that the vapor is in a saturation at a saturation temperature. Remember, in this case, the assumption is TV is saturated. Vapor is saturated. Did you get it? In case of the condenser, the condensation, it is going to further decrease the temperature, isn't it? It will not be a saturation point. It will be, higher than that usually. So that is why even the sensible heat is also accounted in this. Okay. For example, if we assume that the condensate is actually at a saturation temperature, in that case, this factor will go away. Get it?
Yes, sir. It will become TV minus TV.
Yeah. In that case, this factor will go. Okay, so this is all about the condensation. This is all about the condensation, and those who were a little bit worried about the correlations and all, so all the correlations are done. There is no correlations after this. Okay, so we start with the radiation after this. Okay, how much is the time? Okay, so let us start with the radiation. This I have already uploaded on a Moodle, but I will update this corrected one. Some small changes we have made today, isn't it? So I'm going to add this in a Moodle. Okay. So let me just share the another PPT. So I will only browse through the next topic and then probably we will discuss something. Okay. Just a bit. So slides are visible. Hello.
So they aren't visible yet.
Okay. So is it
Yes.
visible now?
Yes, sir.
Okay. So let us start with the radiation. Again, so far we have looked at conduction, we have looked at convection, and now we are looking at a third mode of heat transfer, that is nothing but radiation. And as we started in the very first class that it is slightly different than the conduction and convection. So if you look at the radiation and if you compare it with the conduction and convection, in conduction and convection, heat is transferred from one point in the medium to another in the presence of the temperature difference. So temperature difference is must. Temperature difference and the medium is required in conduction and convection. But when we talk about the radiation, heat transfer does not need a temperature difference and medium. So it is not required. Temperature difference is not required and not is required. Okay.
So your internet is like very poor. Can you just disconnect and connect again?
The radiation heat exchange between two bodies at different temperatures result in a net heat transfer between the bodies. Hello, am I audible now?
Sir, I think you can turn off your video. That would help.
So now I have changed the another network. I just started my mobile network. So am I audible now?
Yes, sir.
Seems to be okay. Okay. So this IIT network is messing up big time these days. So sorry for the interruption. Let's hope that it will work reasonably. Okay. So is it visible? The slides are visible now?
Yes, sir.
Okay. So what I was saying is when we look at conduction, convection and radiation, there is a basic difference between conduction, convection and radiation is when we are looking at conduction and convection, the temperature difference is required. Okay. Temperature difference is required for heat transfer. This word is very important. Heat transfer. Okay. Temperature difference is required and medium is required for conduction and convection. But when we talk about the radiation, we don't require a temperature difference and we don't require a medium. But net heat exchange between hot and the cold body is primarily because of the difference in the temperature. Net heat exchange. What I mean by net heat exchange is basically if you look at the hot body like which is shown here at 500 degrees Celsius and the cold body which is at 100 degrees Celsius, both are transferring heat to each other. Temperature difference. So there will be a net heat transfer. So more amount of heat will be radiated by a hot body, lower amount of heat will be radiated by a cold body, and therefore a net heat transfer will be from hot body to a cold body, isn't it? But temperature difference is not required for the transfer of the heat. Transfer of the heat, you don't require a temperature difference or a medium. Is it clear to everyone? Am I audible? Hello? Hello?
Yes, sir. Yes, sir. It's clear.
Okay, I'm sorry. Okay. So actually I'm on the slide, so I'm not able to see the MS Teams screen. So therefore, sometimes it becomes difficult for me whether I am, audible to students or not. Okay, anyway. So let us look at some more important point about the radiation. Anyway, all these things you have done in your JE days. So there is nothing much which I can add here. But just for the sake of continuity, we will start from the basics, and as we move along, some complications will be added. Okay. So radiation plays an important role in many heating and cooling operations and equipment such as combustion of fossil fuels, operation of furnaces, thermal cracking, etc. Radiation becomes significant when the temperature is considerably different from that of the ambient. So this is a very important factor. So when the temperature is much higher than the ambient temperature, in that case, radiation heat transfer becomes significant, and one has to account that. So thermal radiation emitted by a body in the form of electromagnetic waves. So this is important. Thermal radiations are emitted in the form of electromagnetic waves, and bodies at all temperature except absolute zero emit radiation. So all bodies emit radiations except at the temperature equals to absolute zero. Again, emission of radiation occurs from the surface of a body and propagates at the speed of light. Okay, so the radiation propagates at the speed of light, which is given as 2.998 into 10 raised to power 8 meter per second. Again, the radiation or an electromagnetic wave is characterized by its wavelength lambda or its frequency nu, such that C equals to nu lambda. This is very important. Okay, so radiation of an electromagnetic wave is characterized by wavelength. So what is important here is wavelength and frequency, and multiplication of wavelength and frequency is equals to the speed of light C. Again, emission of radiation from the body is not continuous. So emission of radiation from a body is not continuous, but it occurs in the form of discrete quanta. Each quantum has a energy equals to h nu, where h is a Planck's constant. So that is given as 6.625 into 10 raised to power minus 34 joule second. Again, emission of radiation from body is related to the oscillation of transition of electron in the molecules or atoms. So basically what happens is there is a oscillation or the transition of the electrons is taking place, and because of that the discrete amount of energy is radiated from the surface. That is what it means. Okay, is it all right? This is all you have done in your maybe in first year or maybe in your JE days. Hello?
Yes.
Can we move? Okay, yes. Okay, so this is a very important point to look at. So if you look at the radiation, a body emits radiation in all frequencies and wavelengths. So if you look at the wavelengths, that varies from 0 to infinity. 0 to infinity. Between that, all bodies emit the radiation between the wavelength 0 to infinity. But why some light is visible and why some light is not visible, why some waves are electromagnetic radiations are visible and some are not visible, the reason behind that is, for example, the sun appears bright to us because even though the sun is emitting the radiation in all wavelengths from 0 to infinity, but predominantly the wavelength is between visible range between 0.4 to 0.7. In this particular region, most of the radiations are emitted from the sun are present in this particular region, predominantly in this particular region, and therefore the sun appears bright to us. But in comparison with that, if you look at the earth is also emitting the radiation in an infrared region. But that is not in a visible range. If you look at the wavelength of these infrared radiations, these are not in a visible range, and therefore we are not able to visualize the radiation emitted by Earth. Okay. Okay. Again, one more important point to note down here is energy of the electromagnetic waves varies inversely with the wavelength. So what it means is, if you look at the gamma rays or a cosmic rays, these are going to have more energy compared to ultrasonic waves or a radio waves, etc. Okay. So basically energy is inversely proportional to the wavelength. So that means if I take 1 upon 10 raised to the power 10, then it is going to be a very low value compared to if I take 1 upon 10 raised to power minus 8. So the electromagnetic energy of the electromagnetic wave varies inversely with its wavelength. Long wavelength radiation has lower values of energy, and a shorter wavelength waves has higher amount of energy. Okay. So thermal radiations incident on a body tends to increase its temperature. Depending on the nature of material constituting the body and its surface characteristics, the incident radiations may be absorbed, reflected and transmitted, which is shown here. So there is an incident radiation. Some of this may be reflected, some of this may be absorbed, some of this may be transmitted. Okay. Again, the light falling on a opaque body is mostly absorbed. So if you take a opaque surface, most of the light or the radiations falling on it will be absorbed. On a polished surface, most of it get reflected, and if you are having a permeable surface, then most of it is transmitted. Okay, so reflection can be specular, where the angle of incident is same as the angle of reflection. So that is shown here. So this is a specular reflection where the angle of incident, this phi, is same as the angle of reflection, whereas it could be a diffused one also, where the reflection takes place in all directions. So as shown here, so this is the incident radiation, whereas the reflected radiation is in all the direction. The fraction of incident radiation absorbed by a body is called as absorptivity. So how much amount of radiation is being absorbed is given by the absorptivity. The fraction of the reflected one is given as a reflectivity, and similarly the fraction which is transmitted is given as transmissivity. So the summation of all three factors is equals to 1. Again, there is another property. So other than transmissivity, absorptivity and reflectivity, there is another important parameter which is regularly used, and that is emissivity. So emissivity of a surface is a measure of how good it is an emitter. So emission is different than the reflection. Again, so don't get confused here that the emission and the reflection are different. So reflection is basically whatever is the incident is there, if that directly got reflected, that is reflection. But emission is based on whatever the temperature its body is having, it emits the radiation by its own. So that is the emission. So emission and the reflection are different. Okay. Now let us look at an important concept, that is a concept of black body. So black body is the surface that has the following properties. A black body completely absorbs the incident radiation corresponding incident radiation respective of its wavelength. A black body is black because it does not reflect any radiation. So you can clearly see here the incident radiation which reflects inside, and in all this reflection there is a absorption takes place finally to absorb the light completely. So that is what is occurring here. So since no light is reflected out of this particular body, it will appear black, and that is why a black body appears black, because it absorbs all the radiant radiations. A black body is a perfect emitter, so no other surface can emit more radiation than a black body, provided that they are at the same temperature. The emissivity of a black body is taken as epsilon equals to 1. So black body is a perfect emitter. Emissivity of the black body is equals to 1, and at a given temperature, the black body, no body will have a higher emission than the black body. Okay. So emission from a black body occurs in all directions. So black body is a perfectly diffuse emitter. So what it means is, so emissions are taking place in all directions. Okay, sorry. So black body is an ideal absorber and the emitter. That is what I said. So black body will have a emissivity equals to 1 and the absorptivity equals to 1. Again, it serves as a standard with which a real surface can be compared in order to determine how good the surface is an absorber or as an emitter. So black body is the ideal surface, whereas all other real bodies are compared with respect to the black body. Okay, so now let's look at the real surfaces. So in real surfaces emit less than the black body at the same temperature. Hello? Hello?
Yes, sir. Sir, I wanted to ask, will we say that a black body does not transmit any radiation as well?
No, it absorbs everything. So that is why absorptivity is 1. If it is transmitting something, then absorptivity will not be 1.
Right, sir.
Remember alpha, tau and delta, that is equals to 1. So if alpha is 1, then the other factors has to be necessarily 0.
All right, sir.
Okay. So real surfaces emits less than the black body at the same temperature. So that is what we are saying. The black body is the ideal body, which is going to have the highest emission at the given temperature, and all the real surfaces will have a lower emission at a given temperature compared to a black body. Further, emissivity and the absorptivity of the real surfaces are less than 1, and these may vary with temperature and wavelength. This is very important. If you are looking at the real surfaces, their emissivity and absorptivity may vary with temperature and wavelength. Okay. There is another body which is in between real and the black body, and that body is referred as a gray body. Okay. So this word is actually I think they have just literally given that name, a gray body. Okay. So gray body is in between the real body and real surfaces and a black body. Why we are saying that it is in between real surfaces and black body is in a gray body, emissivity and absorptivity are less than unity. So unlike the black body where the absorptivity and emissivity are equal to 1, so that is in a gray body less than 1. But unlike the real surfaces, these are independent of wavelength. These are independent of wavelength. So somewhat ideal. That is what is been written. So gray bodies are somewhat ideal. These are not ideal. Ideal is a black body. Okay. Is it clear to everyone?
Yes, sir.
Okay. So I think we will stop here. We will start from the Planck's law and other things in the next class. So we will start from the Planck's law. So just Planck's law, maybe I'll just quickly give a description here. The Planck's law basically gives, okay, maybe we will do it in the next class. Just let it be. Okay. Okay. So I have more or less I have gone through your suggestions and your comments and everything which you have marked in your midterm review. And many people have overwhelmingly, given their, their views on how the course is going on and how we can, improve. And I take all your suggestions very positively, and whatever we can, do to improve this course is always welcome. Okay. So the the important comment, most of the people were commenting on the evaluation policy. So some students are saying that the evaluation policy is being changed multiple times. I wanted to clarify that the evaluation policy we have not changed till the last class. I have only asked your suggestion whether it is going to be okay for you or not, isn't it? So we are fixing that evaluation strategy today. So until today we have I have only coined that whether we should have this type of evaluation or not, and I have I have taken your suggestions on that, and if it is okay for all of you, then we will go ahead with that. That is what I said. Okay, so it's not that we have changed at multiple times. We have only said that whether we should go in that way or not. And if you say so, then we will go in. Okay. So the I think many people are okay with this, best 2 out of 3, except 1 or 2, but this 1 or 2 student will always be there, isn't it? No matter whatever I will do, no matter, anything I will do, I will not be able to please everybody, isn't it? So one or the other will be unhappy at some point of the time. That is inevitable. You cannot, eliminate that possibility. Okay. So, but my view is I should take that path which is beneficial to most of the students, not for the outliers. 1 or 2 students is not I am looking at. I am looking at the, most of the students, isn't it? So considering that view, what I feel is base 2 is the policy which most of the students are, not most, I am saying almost 96%, 97%, 98% I can say students are okay with that. So we will go ahead with that unless you have any, question to say or something to say on that. Is it all right? Is it all right?
On which you are going on?
Base 2 out of 3. That is what I'm saying.
Okay, sir.
Base 2 out of. See, I have only relaxed the. I have not restricted. See, there are many people are writing. I can any day say that okay, we will stick to our original policy. That is going to be more restrictive, isn't it? I am only giving you the relaxation. I am giving you more, opportunities rather than, making it restrictive. That I think it's fair. It seems fair. Anyway, those who have scored well in minor 1 or minor 2, they might be having some apprehensions regarding this, but they are also getting one more chance to score more, isn't it? I am not, robbing them. I am giving an equal chance to them also, isn't it, to score more. Correct. So it is fair. In a way, it is fair. Is it okay? Perfectly all right?
Yes, sir.
So if you are not happy, some of the students, if they are not happy, I am really sorry. But see, it is not possible to accommodate each and every suggestion. It is impossible. I am open to take most of the suggestions, but some suggestions are conflicting, isn't it? There is a large section of the students who are okay with that, and there are 1 or 2 which are not okay with that. Then I only have to select a option which is, okay for most of the students, isn't it? So in that sense, I'm sorry if it is not going in your way. I'm totally, sorry on that, but please, bear with us, and, you are also getting one more chance to score. That is what I'm saying. You can, further improve your marks. So it's perfectly all right, isn't it? Other than that, another interesting comment was there from the student that can we make it subjective? I'm really sorry. It's not possible to make it subjective. Subjective is not possible. Why it is not possible? Because see, I generally give the subjective paper in all my other elective courses. I give subjective paper. And there the reason for giving the subjective paper is the students are around 35 to 50. Checking 35 to 50 copies on a computer is not difficult. I can do it. There is no problem. But here we are talking about 200 copies, isn't it? And even in those 35 and 50 copies, I very commonly I have seen people have copied from their friends. See, even though I am on this side, but I have been a student at some point of the time. And I understand all the tricks, isn't it? It's not that I am coming from some moon or something and I have not seen those tricks. I have seen those tricks, isn't it? So I understand. So I could easily see that, it's not going in a noble way there. But considering that the limited number of students are there, I can still go ahead with the subjective type of evaluation there, because such outliers are 1 or 2 there, isn't it? But considering 200, it is going to be really difficult, not only in terms of checking on a computer, but also in terms of, restricting this uh, um, this unwanted, copying and all these things. It is really difficult if I give a subjective thing. Okay, so subjective is out of question. Other than that, there are different options people have given. I will, try to accommodate those if possible. I'm not, promising you, because the paper, how I can make a paper, that is my prerogative. Hello. Hello.
Yes, sir, you're
Hello.
audible.
Okay, so basically what type of question paper I wanted to set or something, that is my prerogative, isn't it? Please, I will, try to do whatever thing is, better for most of the students, but don't expect that, it will be subjective or anything. I wanted to be as fair as with, everybody, and within that constraint, whatever is possible, I will do it. Only I can promise that. That's it. Okay, is it okay? Perfectly all right.
Yes, sir.
Okay, so thank you again. Thank you everyone for, writing a lot of suggestions, and I take your suggestions very seriously. Okay, I take your suggestions. I go through each and every comment written, line by line. Okay, so if you still have some suggestion to make or something, it is going to open till tomorrow. Please write it. There is no problem. Uh, and I will see how much maximum I can accommodate. Okay. Thank you so much. Okay, see you. So we have tutorial Monday batch. Uh, uh, so the Tuesday batch, do you wanted to have a tutorial tomorrow, or you will be coming today?
Sir, however it's convenient to you, it's fine. Because the tutorials have already been uploaded long back.
Yes, I have uploaded all tutorial. Okay, we will see. We will see. If all the students are around, then probably we will only have a tutorial on Monday and no tutorial on Tuesday, because it is kind of, repeating the same thing, and very few students attend on Tuesday. So I have no objection in doing it again. But then the students are less and they are only relying on the recording. So it is unnecessarily increasing, my workload, isn't it? Okay, guys, see you then today. Okay. Thank you so much. Bye.